Okay, so the next speaker of today is Yucheng Yang, talking about heterogeneous agents. So like it's also nice he recently accepted a job in Switzerland. So like we increased the brain power on that field here. So like thanks for making the time today, Yucheng.
Sure. So thank you so much to the organizers for inviting me here, and also it's a great pleasure to teach my paper on using deep learning to solve heterogeneous agent model with aggregate shocks. So this is a very much method-focused conference. So I think when we develop some new methods, it's important that this method is cool and powerful. But also, I think it's also be nice if the method is very helpful in terms of helping us addressing important questions of our time, or even pushing forward the development of some economic field. So, I'm a macroeconomist. Let me start my talk by quoting Richard Rogerson, who has been the head of the boss of the macro group at Princeton, where I graduated from for many years. So Richard said that the major focus of macroeconomics over the past 20 years has been the development of models that incorporate rich heterogeneity and frictions that can simultaneously speak to aggregate outcomes, but also addressing a rich set of cross-sectional facts. To study this kind of heterogeneity issues in macro, so the main workhorse model in this class of problem is a heterogeneous agent model with aggregate shocks, which is very well known to have some significant computational challenges for many, many years. So these kind of models are usually solved with two kind of methods. Firstly is a global solution method pioneered by Kursel and Smith, so which is now called as Kursel-Smith method. Or when it's very hard to find global solution methods to this kind of problem, people usually go to these kind of local perturbation methods, in the spirit of like Dynera, which many of us are very familiar with. So there are both important progress, but also some limitations of both of these methods. So for the global solution methods after Kursel-Smith, since it's global solution, it's helpful to addressing questions with large shocks, to study questions where the global dynamics is away from the local deterministic steady state, or we can handle lots of nonlinearities like zero lower bound we used to have for a couple of years. However, this kind of global solution methods I will illustrate more later. We need to handle the whole distribution. At least we want to handle the whole distribution directly in a state vector, which makes it computationally very costly. So as a result, it's very hard to use Kursel-Smith method to study sort of modern quantitative models, with multiple shocks, multiple endogenous states, or further do rigorous estimation or calibration in this kind of models. In recent years, there has been lots of development, in these new models with heterogeneous agent, and usually people are using perturbation methods to solve them. So those methods are pioneered by work by Michael Ryder in 2009, and also the recent influential work by Auclair, Bartolozzi, Roney, and Straub. So this kind of perturbation method, essentially, we want to first solve the steady state of the problem with no aggregate shock, and then we want to perturbate around this around this deterministic steady state with respect to aggregate shocks. This kind of methods is very efficient to solve because essentially it's a log linearization around some high dimensional point. So it allows us to study more advanced models with all these elements. But as a local perturbation method, it's very hard to discuss large shocks, risky steady state, or nonlinearities with respect to aggregate shocks. So with all these advantages and limitations in mind, so in this paper, so we developed a new deep learning based global solution methods to study heterogeneous agent model with aggregation. So following these 2 days talks, I think many of you now know deep learning is useful in terms of study high-dimensional problems. So, but I think for teaching purpose, it's always useful to repeat the important things. So let me just sort of explain my understanding about how to use deep learning to solve high-dimensional models. Use my language so that you can have sort of a better understanding of these issues. So, so here, in this project, we want to use deep learning to learn the policy and value functions in a heterogeneous agent model. And to my understanding, there's always to learn some high-dimensional function using deep learning. There are always three key steps. The first step is to use deep neural networks to represent the key function of our interest. Here in this setting, this is a function for value function and also policy functions. I don't need to explain this architecture of neural networks. So I think you all know this. And then with this function representation, we want to cast these functions into some objective function. So as Simon just mentioned in his talk, there are multiple different ways to set up an objective function, which people have lots of debate, which I think is nice thing. So people just try different ways to formulate the objective function. Then once we have a representation and also we have objective function, we just want to sort of adjust the parameters in my high-dimensional representation to maximize or minimize my objective function. So this procedure is obtained by doing some efficient optimization algorithm, which is usually done with stochastic gradient descent methods on some mini batches. So as Jesus mentioned, so these three procedures are actually very essentially the same for any kind of function approximator when we want to solving some economic model. So we can use these F terms here can be deep neural networks, but it can also be polynomials that we previously see in the computational macro literature. But here I would say because of the advantage of deep neural networks in terms of the strong representation capability and also this very efficient optimization algorithm, so that neural networks is more efficient than the polynomial-based approximation we previously seen before. Okay, so in this project we are going to use this kind of idea to solve heterogeneous agent model. So essentially, we are going to use neural nets to represent the value and policy function. So in particular, I'm going to show later that, so we are going to design the architecture of the neural nets. So essentially, we are going to use a subpart of the neural network to represent, the state distribution, which is, this gigantic object in the state vector we usually see in heterogeneous agent models. Then, once we have this particular design of neural nets, we are going to do something very similar to what John taught in the first day about value function iteration. But I'm going to tell you that there are some difference there, which is actually very important difference. Okay, so in the paper we apply the deep. So this is new method. We call this as deep ham. Sometimes we try to come up with these nice acronyms to differentiate our work with a deep equilibrium net or other nice work. So in the paper we apply deep ham to three questions. The first question is the standard Kurzweil-Smith problem, which is a competitive equilibrium problem in the Kurzweil-Smith model. And then in the paper we also solve the problem, what we call as a Kurzweil-Smith problem with the financial sector. Essentially, it's a Jesus econometric paper model. So then, as a new application in the paper, we also solve for the constrained social planners problem in heterogeneous agent model with aggregate shocks. So this is a very well-known computationally challenging problem in the heterogeneous agent model literature, and we find that our deep ham method is particularly suitable to solving this class of social planner problem. Okay. Now, so now let me illustrate the deep ham method. Explain the deep ham method by using the simplest heterogeneous agent model with aggregate shocks, which is the Kurzweil-Smith model. So I think that the macro people in this room is going to be very, very familiar with all these settings, but I will try to go through it quickly so that because I think we do have people from other fields joining here. So the Crusoe-Smith problem is a production economy with a continuum of households. So each household is going to solving this lifetime utility maximization problem subject to the following household budget constraint. So here the households, so the YIT term is households employment status, so which is exposed to idiosyncratic shocks, which is IID across different households. You can think about this process as some finite state Markov chain, which is IID across households, and so this wage rate and also gross asset return, so is determined by by a representative firm problem, which use this sort of standard production technology. So with this ZTS aggregate shock, which also follows some finite state Markov chain process. Then the first order condition of the firm's problem is going to determine these factor prices for wage return and also gross capital return. So that the aggregate shock is going to affect the household's problem through these factor prices. And because there's aggregate shock here, the factor prices are uncertain over the time. But the households may always want to know this stochastic process in the future to make their optimal choice for consumption and saving. So usually when we solve this kind of problem, we want to write them in a recursive form. Then immediately we can see the curse of dimensionality shows up. So here, when we write down the recursive form of this Crusoe-Smith problem, so we would see that, so in a state vector of household I, it not only includes its own individual asset and also employment status, but also the aggregate shock, but also the whole distribution of all the asset and also employment status of all the households in this economy. So the reason that, so this gamma term, this is an infinite dimension distribution object of shows up in this in a state vector is because the households, they always want to know this gamma term so that they can predict the future factor prices to make the current policy decision. So which makes this problem as sort of a infinite dimensional dynamic program problem. So we know that we cannot solve infinite dimension problem even with neural network. So of course previously when we can only solve like low dimensional dynamic program problem, so people come up with this smart idea of what now we call as Crusoe-Smith method. So essentially we want to approximate this very high dimensional state vector with some approximate state. Obviously the most natural way to approximate a distribution is to use the finite moments of this distribution as an approximation. So essentially in Crusoe-Smith 98, they try to use the first moment of the whole asset distribution to represent the whole distribution. So, but when we have this approximate state vector, if we want to write down the Bellman equation, we're still missing something. So which is we need to have a law of motion for this moment representation. So at this equation, we don't need a law of motion here because when you know the distribution of everyone, you essentially, if you also know the current policy function, you can apply the policy function to everyone's state, then you immediately know the next period distribution. But if we approximate this distribution with first moment, we also need to conjecture some law of motion for this dynamics of the first moment. So in Crusoe-Smith method, they use a log linear function form for this dynamics of the law of the first moment. Then essentially this algorithm of Crusoe-Smith method goes, we start with some initial guess of this log linear law of motion. Then given this law of motion, we solve for this sort of 4-dimensional dynamic program problem. Then once we get this problem solved, we can simulate the economy forward to update our guess of this law of motion. then we sort of iterate until we get some convergence here. So this Crusoe-Smith method works very, very well for this kind of simple setup, but it's very, very costly when you have sort of more than quantitative heterogeneous agent model, when you have multiple assets, when you have multiple shocks and so on. So of course, now we are here in this deep learning summer school, we want to, revisit this problem, try to, use deep learning to directly solving for these high dimensional value and policy functions. So before presenting the, this general procedure of DeepHam, let me first tell you how, we handle this distributional object in this heterogeneous agent model. So let's first consider sort of a finite agent version of this Crusoe-Smith problem. So N is finite but large to approximate the continuum of agents. So the general form of the value and policy function is going to be like the following. You can see that in the state vector, we have my own state, but also everybody else state here. But we know that there should, in this kind of Crusoe-Smith model, so because the agents are so-called ex-ante identical, before all these shocks hit, the agents are actually, ex-ante identical. So which sort of means that, for if I am agent I do not really care about the particular order of other agents. I only care about, sort of the distribution of other people in this economy, right? So which means that, so this vector of other people's state affect me only through some, through distribution, which means that if we can come up with some sort of symmetry preserving representation for the whole distribution, so we are not going to lose much information for this problem. So this motivates us to approximate, this problem using, by introducing something we call as symmetry preserving generalized moments. Essentially, we are going to, use some basis function Q. So we are going to map everybody's individual state to this Q of this state. Then we are going to take the mean of all these Qs. Okay. To give you a better understanding about, what this average thing could means, if we take, Q as identical mapping, then essentially we just get the first moment. But of course, if we parameterize this Q with, for example, with neural nets, this is a low dimensional neural nets, right? So each of these Q is just a one dimension to one dimension mapping, right? So if we parameterize this Q with some, flexible nonlinear function, we can get things like which is more flexible than first moment, but also sort of capture some information from the distribution that matters for, our policy and also our value functions. So essentially, in this kind of heterogeneous agent model, so many people try to derive, analytically based sufficient statistics, and our understanding about, we can actually, try to ask the algorithm to come up with a Q, and then we can see that what are those average Q means. So which is sort of making like numerically determine sufficient statistics. So because of the low dimensionality of the Q, we're also looking to the function form of this Q to get some interpretability about how heterogeneity, how distribution matters in this kind of problem. So I'm going to show you more later. And of course, so there should also be some nice theoretical properties of this Q. So you will learn more from Jesus in his talk in the afternoon. So I'm not going to touch upon the theoretical part of this issue. Okay. Now with this, deep learning based distribution representation in mind, I'm going to show you the general procedure of the DeepHam algorithm.
Can I ask a question?
Yes.
So if I understand correctly, so if you are going to estimate this type of model, then I guess asset distribution is essentially observable in the data. So how is it different from like estimating some sort of non-parametric density of asset first, and then given that like we can, estimate the model. So like why do we need this generalized model, not just a simple non-parametric density estimate?
So this is a great question. So so here we are not estimating the Q from the data. So essentially we are trying to get the Q as part of the algorithm. So Q is one way, actually it's going to be nice if I get to this question after this slide, because I am going to tell you that Q is one way that I design my neural network. So I'm going to have a neural network for the policy and value function, but I'm not going to, so this policy and value function are not a direct mapping from the distribution gamma to the output, but it's sort of first a mapping from the distribution gamma to the generalized moment. Then, we have a mapping from the generalized moment and other things to our policy and value outcome. So this is essentially sort of some economic informed restriction on the architecture of neural network. So the Q object is part of the algorithm instead of part of the estimation from the real world data.
So Q does differ across agents, right?
No, the Q function is identical across agent. It's just a function.
So it's like subscripted Q1 through Qj.
Oh yeah, so here this subscript means we can have multiple generalized moments. But the number of generalized moments is usually way smaller than the number of agents, which means that there is a dimension reduction thing here from this line to this representation. Okay, good.
And Q does contain something, right? Like are there parameters in Q, like maybe not the ones we care about, are there parameters there?
So Q, so in our sort of the general version of DeepM, Q can be parameterized directly by neural nets. Then we solve for Q, but we can also try to pre-specify what is Q here. Let me get back to you after I talk about the next slide. It's going to be answer both your question and your question. Okay, so.
Yes, like a brief, so just a clarification, I understand correctly that the number of these generalized moments that we fix ex ante, right? It's not going to be.
Yeah, it's also a hyperparameter we need to try. It's like that, we tuning the architecture of the neural net.
Can I ask another question?
Yes.
I think on the previous slide you've mentioned that here, yes, that the agents will not have to form any beliefs about the evolution of gamma. Can you come back to that?
Yeah, so
I mean, they have to have some beliefs about
Oh, yeah,
the
yeah.
segregate state, however complex it is, it will future.
to be very precise, when we have this original form of Crusoe-Smith model, when we define the equilibrium, of course, so the agents do have some belief about the law of motion. But my point is that here, when we solve the problem in this form, we do not need to have a conjecture to perceive the law of motion for agents. So it's like there is some consistency condition when we define the equilibrium that the agent has some belief about the evolution of distribution. And finally, in the economy, there is some law of motion. And these two things, the belief and the real law of motion, are consistent with each other. So it's like we do not need to take some law of motion as given to solve the problem, or sort of low dimensional law of motion as given to solve the problem. Okay.
Should we think of these generalized moments like Chebyshev bases, where when I have a new J, I need to recompute everything? Or should we think of them like something like mean variance, where I could just add one more?
So in fact, when we hyper tune this capital J, we are doing the first option you mentioned. Okay. So we just, because we find, in Crusoe-Smith, we find the competitive equilibrium of Crusoe-Smith, we find J equals to 1 is enough. But for other applications, we find probably we need J equals 2, J equals to 3, which improves the accuracy of our method.
And I guess I'm asking, every time I change J, all of my moments, right? I can't reuse what I had.
Right. All the moments are changed. Okay. Now let me talk about this general procedure of DeepM. Then I guess you can clarify lots of some of your confusions. So again, we are solving a discrete time version of this n-agent heterogeneous agent model. Our key object of interest are the value and policy function parameterized by, so we are going to parameterize them by neural nets. So these are mapping from, as I say, so from our own state aggregate shock, but also the distribution to the value and policy outcome. So here, because this is an n-agent version of the problem, so this is going to be a finite dimension, even if it could be very high dimension. Then we are going to parameterize this mapping into two parts. The first part is, where we get the Q. So we are going to map this distribution object to some, a couple of generalized moments. Then in the second part of the mapping, so we are going to map this, individual state, aggregate shock, and generalized moment to the value and also the policy outcome. Okay, so you can see that those two parts of mapping are sort of parameterized by neural nets. In the first part, we have this Q term parameterized by neural nets. And then the second part, we map this low dimension object to the value and policy outcome also through neural networks. But it's like we have a big neural network with lots of parameters, but it's sort of nested into two parts of the mapping. So we are going to train the big neural network altogether. It's instead of train these two parts separate. Okay, so then this is a representation. So with this representation in mind, so we are going to do something in general very similar to value function iteration. So in the first step, so we are going to do this in iteration. In the first step, so we are going to simulate sort of the current ergodic distribution with the most recent policy, because this is a very high dimensional problem. So we cannot do this accurately on all the grid points. So we essentially simulate a bunch of lots of samples to make sure our objective function is sort of well perceived on those samples. Then given the current policy function, we are going to update the value function. So this step is sort of standard, so I'm going to skip it without talking about the details. Then given the value function, so we are going to optimize the high dimensional policy function on simulated paths. So this step is going to be a bit different from what we commonly see in macro models, and I'm going to explain them in some details. Okay. Yes.
I just have a quick clarification question on the architecture of the neural net. So for that Q here, let's say if I want to make two moments, then that would be like, and I have 10 state variables. So it would be like 10 input and 2 output neural nets, or it would be 2 subnetworks.
You mean 10 state variable mean like 10 assets?
Yeah.
Oh, so when we do that, we actually we have generalized moment for each of the asset. So it's like we have like a 10 times 2.
So then you will miss the correlation between the assets, because you don't take into account the.
Yeah, you can also try to get some yeah, you can also try to get some interaction of that, but we haven't tried that part yet.
I have another question about the first step. You say you will simulate stationary distributions.
Mhm.
So, but at the very beginning, your policy function is randomly initialized with your network, right?
Yes.
So when you do the simulation, could it be never stationary?
Sorry.
So because your policy function.
I have some like sort of educated initial guess, right? So then I essentially simulated the stationary distribution, which is sort of I can show later, which is sort of a starting point for all the simulation I'm gonna do later.
Okay.
But yeah, that's gonna be based on my current policy.
So you are simulating a policy and you use the neural net to approximate that policy? Or
No, so you mean at the first step,
Yeah.
at the initial step? At the initial step, I just, because this is a simulation part, right? So at the initial step, I just, usually, so here, we usually use some constant share for saving decision as an initial guess. Then we simulate the economy, with idiosyncratic aggregate shock to simulate all these agents forward for multiple period until we get some ergodic distribution based on the current policy guess. That's a initial distribution for sampling.
Okay, so the first round of simulation is not using your policy function. It's using some other kind of.
Now the first round is based on initial guess.
Okay.
The initial guess could be, constant share of policy. Yeah. Yes.
Just some brief additional questions. So for example, if I were to assume, okay, the model that was also employed endogenous labor supply, then would just make this step 2 mapping from these states to like value function that would just be then like a neural net with 3 outputs instead of.
Yes. So with endogenous labor supply, so there are multiple ways to do that. So with endogenous labor supply, it depends. So in all these methods, we want to make make the question that's solved by neural network as simple as possible. For example, if we can explicitly write down some sort of intratemporal, labor supply conditions that make labor supply as a function of consumption, then we'll definitely only solve for consumption and then use that analytical condition to get the labor supply. But of course, you can imagine that we can also put labor supply here, but just try to achieve another optimality condition. But we always want to make this problem as simple as possible. Try the best to make use of other analytical conditions. Yes.
Two questions. First, when you say parameter has 2 parts of the mapping, are you specifically referring to like the economic parameters, like that you have in the first order condition, kind of like the way Simon was talking about it, or these? Like,
so here the parameters. I think so far most of the parameters I'm talking is about the parameters in the neural nets. So I guess I should be more specific. It's a neural network parameter. It's a weight, sort of weight and bias. Usually I don't use that.
Thank you. My second question is, so when Simon was talking about simulation, he's exclusively talking about simulating on the policy function. Here somehow you're, well, essentially, where is the value from this? When Simon was talking about it, he was not really doing anything with value. You are, so like, how is the value function fitting into this?
So you can see that in the next slide. So or 2. So you can see it. Yes.
Sorry, there has to be that with the Q that was updated together with the
yeah. So you can see that. So this is like a big neural network. Map the original input to value and policy outcome. But the neural network is parameterized in a way that it is first to map the distribution to Q, then map the Q to output. So all these neural network parameters are optimized at the same time. It's just like a particular architecture of this big neural network. Okay, now let me explain what we do for policy function optimization on the simulated data. Okay, so let's imagine now we are in the case iteration of this algorithm. So we now know that the current guess of this of the value function. Then we want to optimize the new policy function. So for this n-agent version of this competitive equilibrium problem. So we want to, in this competitive problem, so it's like all the agents take other people's, policy as given, right? So we want to solve this problem as so-called fictitious play. So which means that in this iteration, so we are going to separate, the whole problem into like an individual problem, right? But when we solve the ice problem, we are going to fix other people's policy function from, it's like the last play. So essentially, we are going to have multiple rounds of fictitious play when we do this one iteration of policy function optimization. Okay, so at a new round of play, so we know the policy function from the last round. So this is the policy function that everybody but one agent is going to take. Then I'm going to optimize for this one agent's new policy function. So essentially, I'm going to update her optimal policy to maximize this term. So which is the expected term of accumulated utility of this agent I up to period capital T plus this terminal value discounted by beta to the power of capital T. So first, you can see how the value function enters, right? So we have some terminal value function here. Then, how we are going to optimize over this cumulative utility, because you think that my cumulative utility up to period capital T is something that not only depend on my own decision, but also everybody else's decision in this economy, right? So we are going to optimize on this thing in a computational graph that is on this slide. So essentially, for a certain agent I, so I'm going to have some policy function I want to optimize on, and other people, other n-1 agent in this economy is using their policy function from last round of this fictitious play. Then, with all these policy functions for everyone, I can simulate the economy, to period capital T, right? So because in this kind of Crusoe-Smith problem, once you have everybody's policy function, you can simulate the economy forward, because all these prices are explicit function of your individual states, or will be determined when you have your policy function. So essentially, if I can simulate the economy forward, so this cumulative utility term is just going to be sort of a differentiable function with respect to all my unknown parameter in my policy function neural network. Okay, so this is the essential idea of how we are doing this policy function optimization here, because this objective function is sort of differentiable to the unknown parameter in my policy function neural network. I can use stochastic gradient descent to sort of change my policy function parameter so that I can improve my objective function. Okay.
If you go one slide back.
The graph, or
yeah, no, we can also do that. The state contains, you just said the state contains gamma, which is the distribution over there, right? But that is not gamma in itself. It's represented by the moment, right?
Yeah, it's a original gamma. So I think it's clear in the computer graph. So here, this state, so is this S here? The S is just the gamma. It's just a gamma. So this is essentially everybody's individual state. If I want to simulate the economy forward, I need to know everybody's individual state and then apply either sort of the unchanged fictitious play policy from last round, or with my sort of the variable policy function of agent I.
So what is the state? Is the state gamma, or is it the representation of the state?
So here, this thing is a state. It's a gamma. It's a whole distribution. Again, I want to say so. The Q thing is just part of the neural network policy function neural network. So essentially, what we finally saw is these two objects, the value function and policy function, defined on the original state vector. Okay. But so these are parameterized by neural nets, but the neural nets is sort of have two components. Has two sort of nested components. One is the mapping from distribution to moments, then match moments to the final outcome.
Okay, maybe I just don't understand. But if you look at 2 here, it just looks like the value function is given by the moment, right?
Yeah, but it's like we have a whole mapping, right? So we are solving for this mapping, but we are putting some restriction on the function form of this V and S, also V and C here. Okay, I guess, yeah.
Can I ask, will you show the exact architecture point? Because like the computational graph you had, this reminds me like heavily on the current neural nets, sort of like you have time t, or like long short-term memory.
No, in this project we do not have a. So this policy function is time invariant. It's every period I'm applying the same policy function on agent. When we solve like a finite horizon problem, the policy function we solve is going to be time dependent. Even it looks like recurrent neural network or something, but essentially here we are applying the same policy function neural network to this agent I.
Yeah,
we want to optimize on.
Neural network you would have the timing variance this direction, you have it that direction, right?
Yeah. But finally, it's like this thing is differentiable to all these unknown parameter in the policy function neural nets, right? So my objective function is differentiable with respect to all the unknown parameters in my policy function. Then I can change my policy function neural nets to improve my objective. Yeah, sorry for it.
So can you clarify again? So I thought like when you restart your period, you would use sort of the same policy, the latest policy function for everybody, but because I think you say you don't do that. You use like the previous policy function for the other guys. Is that because you updated the value function and are calculating a new policy function? Or why would you not use sort of the latest for everybody and then do the stochastic gradient, just keeping everybody else's sort of value policy function fixed in order to update that guy's?
Oh, it is. So we are, so here, when we update for this agent I equals to 1, so the other n-1 agent, they are using the latest policy function, but they are sort of using the latest policy function within this multiple round of fictitious play. I think this is exactly what you are thinking about. Because I want to solve for competitive equilibrium, I don't want to optimize everyone's policy at the same time. I'm going to show that that's actually solving another very interesting problem, but not here. So here, I was talking to Felix about how we do, sort of check convergence and also decide the number of runs in this kind of algorithm. So here, essentially, the way that I do this is I just run it for like 100 play. Then I'm going to the next step, the next loop.
The plays, this algorithm doesn't have to be inside the K loop, right?
Yes.
And the entire purpose of the play is just, so essentially you have a given value function, you're trying to optimize the policy function.
Yes.
And you use the plays to do that.
Yes. So you don't need to worry about that. We are wasting not many loops. Essentially, it's like we do one iteration of value function optimization, then we do many sort of round of policy function optimization here. Okay, so I guess it's sort of clear that we are.
So this is a question on that from Paul. So he asks like the idea of separating the neural net into two layers is interesting. The first step, an uninformed dimension reduction of the state space, someone has a behavioral interpretation to me. Croswell-Smith cites boundary rationality to justify the heuristic view of agent only focusing on the mean. Here your approach is essentially Anand tells the agents what optimal dimension to approximate policy value. So,
yeah, I think it's a nice comment about the interpretation about using this symmetry preserving generalized moments. Yeah, I think in terms of I think it's a very nice interpretation. This was also my interpretation when I first see the Croswell-Smith method. Essentially, we are trying to, modeling the way that people think about the whole distribution. I'm not sure whether neural nets is bringing this to another level, to assume that people really has sort of the mind power as a neural network. I'm not sure. Maybe Croswell-Smith is actually a better.
So when I was thinking I thought about just hitting it with an auto and saying, forget about the, like trying to structurally model the moment. I'm not that, like, do you think that would work? Or like, do we need to care about?
I think so this is very related to her earlier question about like thinking about this issue. And I would say there's a nice paper by Frank Schopai, Ming-Su Chang, and Xiaohong Chen. They try to do this kind of, they try to run a sort of a structured vector regression with sort of distribution data. So they use like sieve methods to represent the distribution. But the nice thing about sieve is that you have some nice asymptotic properties. So you can write in an Econometrics paper. I feel autoencoder is obviously also a very nice way to do like dimension reduction. But I'm not sure like it's whether it's going to be better or
then like that's the reduced form of what you're doing structurally.
Yeah. Okay. Yes.
I was wondering how the agents are heterogeneous. So they all have the same policy function, or do you do for each agent a different policy function? And if that is the case, how do they differ?
So here in this class of heterogeneous agent model, the agents, so it's like in the equilibrium agents, they are different, like in their asset and also in their employment status. So this is why we call these things as heterogeneous.
But they have the same policy function.
Yeah, so it's because we want to write the agent in a way that they finally have the same policy function.
Yeah.
You can actually think about models that agents, they have the sort of ex-ante heterogeneous types. Then each type may have their own policy function. But of course, you can also try to rewrite the model so that we make a type as one of the state variable. Then again, this policy function is going to be the same policy function for everyone. It's just
I can
depending on
think of them as identical agents with different initial conditions.
It's with different equilibrium status.
Yeah.
Actually, so in Kurzweil-Smith model, everyone actually starting as sort of identical agents, but it's starting from like 1,000 years ago. Then we have idiosyncratic shock and average shock hits. Finally, in the equilibrium, everybody is heterogeneous. Okay, so I want to say a few things about this optimization over simulated paths. So first of all, get back to Frodo's earlier question that, so here we do not see, so in this algorithm, we no longer see any perceived law of motion because agents, they essentially formulate their expectation for the future prices just through this simulation. Okay? So it's once agent know other people's policy function, can decide on their own policy function, they can know the future path of the prices. So there's no need to introduce additional perceived law of motion here. And I want to say, so this kind of optimization over simulated paths is sort of similar to the idea of doing reinforcement learning. But this is sort of a model-based reinforcement learning. So I think in a reinforcement learning, in many of the reinforcement learning examples we see, like in AlphaGo or AlphaZero, usually this kind of the reward function or the state transition function is something that we learn from the data. But in the economic model, sort of the reward function, we know what is the utility function, right? The state transition function is just given by our household budget constraint. Current asset, and then you can use a household budget constraint to write down the next period of the asset. So which is sort of make it very much similar to the idea of model-based reinforcement learning. And also I want to mention that so I've been talking to Simon about how to pick different kind of objective function in this kind of problem. So here you can see that we are essentially doing something similar to the lifetime utility optimization with some, of course, terminal value function here. So this formulation with this kind of both objective function, but also the way that we optimize over simulated paths is can allow our methods to easily solve the so-called constraint efficiency problem in heterogeneous agent models with aggregate shock. So this class of problem is, say, it's no longer a competitive equilibrium, but it's there. Think about there is a social planner in this economy, and the social planner can optimally choose the policy function for all the individuals to maximize some social welfare objective function. Okay. Then so this is very, of course, it's so you can see that this is very important. This is sort of like the second best allocation in an incomplete market model. So, but previously it's very hard to solve. But for our dependent method, we can solve this constraint efficiency problem as easily as we solve the competitive equilibrium. We sort of just get rid of the fictitious bit. It's just as you say. So we no longer respect other people's policy function. We want, from perspective of social planner, we want to optimize over everybody's policy function altogether, right? So to maximize some social welfare objective. So finally, so this kind of finite agent approximation and plus fictitious place structure can also be used to solve some strategic equilibrium that we are interested in, like some like IO literature. Okay, so I'm going to present some accuracy results. So first of all, we computed sort of the Bellman equation error for the Crusoe-Smith method, and also for DPAM method with pre-specified generalized moment, which is we can first specify the Q function as identical mapping. And let's say like I can specify that, not allow them to change. But I can also use one generalized moment. So it's like to choose the big J equals to 1. I only allow for one generalized moment to train the DPAM algorithm. So we compute the Bellman equation error sort of on the original very large state space. So it's not surprising to see that the Crusoe-Smith method, even of course they are very, very accurate in the approximate state space, like the 4-dimensional space, but it's not super accurate when we look at the original state vector to check the Bellman equation error, on a very large space, state space. Then if we go from the Crusoe-Smith method to the DPAM method with only first moment, we will see some reduction of the Bellman equation error. So here, this benefit is mostly coming from we are still using first moment to represent distribution. Now we have a more flexible way of mapping the moment to the policy and their outcome through the neural network instead of through the grid space. And so if we further allow for the flexible form of this generalized moment Q, we can further get some improvement on this in terms of accuracy. And as I said, so the generalized moments are low dimensional. Yes.
On the accuracy, these standard deviation of the error. So should I interpret this in the sense that the DPAM gives me on average a lower error, but that's more likely to give me like large error because the standard deviation for the
but standard deviation is also very, very small. If you want to test the difference of these two errors, it's going to still be significantly different. But so the standard deviation comes from many different runs of this algorithm. So we find that no matter how you initialize the policy function, you always get a lower Bellman equation error than like the Crusoe-Smith method.
Okay, but the Bellman equation, that's like an average for like over either some grid or like along some simulation pattern case, right?
So the Bellman equation error is, yeah, you're right. I think it's defined on the, oops. Somehow it's not clear. Yeah, I'm not gonna. Yeah, the Bellman equation error is computed it's defined on a very large state space, but it's computed on simulated paths. But it's a very large amount of simulation.
So how is it different from the difference in policy function? Because what we care about is how agents will behave differently. So even though the Bellman error is much bigger, if there's a very small difference in the policy, then it doesn't matter. So why do you care about the Bellman error and not the difference in the policy?
Yeah, it's a great point. So I would say, so in this problem, it's actually well known that Crusoe-Smith method actually solved Crusoe-Smith model pretty well. So the policy function is not that different, but sort of quantitatively it's not that different. But we do see some qualitative, difference in terms of understanding some subtle feature about how we represent distribution. You'll see the next slide. Yes.
The policy error is just like seeing how far the first order comes from 0. But like here.
Well, the Bellman equation error is you write down the original form of the Bellman equation. It's like this one. Yeah, it's like this one. Then you write down the Bellman equation, and then you compute the the loss of this for this equation.
But how do you know, like, you're computing the loss from like the true value, like how do you know what the true value is?
Now, when you solve for the true solution, this thing should be as close to as close there as possible for all the grid points.
Okay. That makes sense.
Okay, great. So yeah, now let me get to about what's a sort of a so it's interesting that usually people say, you know, there's some solution qualitatively we are similar, but quantitatively we are different. But here that for the Crusoe-Smith, because quantitatively is already so well solved by the Crusoe-Smith method. So it turns out we find some qualitative difference in terms of solution. So which comes from the representation for distribution. So as I mentioned, you know, this Q mapping is a very low dimension mapping, right? So we can look into what the Q look like and to get some understanding about how heterogeneity matters in this kind of problem. So this is, you know, the Q function we get, the Q basis function we get when we solve the Crusoe-Smith problem with only one generalized moment. We can see that, you know, the Q function is not a linear mapping; it's a sort of a concave mapping. Then, you know, we also to understand how this Q works, we also need to see the second part of the whole neural network, which is a map from the mean of the Q, which is the generalized moment, to the final value function. So we find that these mapping are actually pretty linear. But this mapping is quite concave. Okay, so we could think about, you know, some policy experiment to understand you know, this generalized moment representation. So if we think about some unanticipated redistribution policy shock, in which, you know, the policymaker is going to take some asset from the richest guys and redistribute that part of asset to the poorest guys. And there are also some people who are not affected, some middle wealth people who are not affected in this policy experiment. Then if we think about how this kind of policy experiment is going to affect the immediate value or immediate welfare of these middle wealth people who are not in the experiment. So if we look at the solution of deep ham, then we can see that if we take some assets from the rich guys to the poor guys, we are going to increase, you know, the value of the generalized moment, right? So which again, if we think about this mapping to value function, which means that for these people who are not involved in this asset redistribution policy, so their welfare should actually going to be decreased. So essentially their immediate their welfare are going to be reduced on impact. But if we think about this experiment in a Crusoe-Smith solution, so in which for all the agents, their welfare is only going to be a function of the current individual state aggregate shock, but also the first moment. Because in this kind of policy, you know, asset redistribution policy, the first moment is not going to be affected. It's just taking some people's money and give it to some other people. Then, you know, the policy sort of the implication on the immediate welfare impact on these people who are not in the redistribution program is that, you know, their welfare should not be affected immediately. But we can think about this issue that so which one actually make more sense, or even sort of make more qualitative sense. Is that if we redistribute some money from the rich people to the poor people, because their marginal propensity of saving into the future is sort of different. So if we do this kind of policy experiment, actually we are going to, you know, change the future path of the asset prices after this policy experiment, which is going to have a welfare impact immediately on the people who are not in the redistribution asset redistribution program. So I think, you know, this sort of say that, you know, this is more consistent with what we can get from the deep ham solution instead of what we can get from the Crusoe-Smith method. So this is something that we can try to learn from this kind of generalized moment solution. Okay, so then I'm gonna use the last 15-20 minutes to talk about using DPAM to solving the constraint efficiency problem. So let's say, so the constraint efficiency problem is sort of the social planners allocation problem in incomplete market models. The social planner need to respect all these market incompleteness constraints, but they also want to pick up the policy function for everybody, every individual household. So this is usually referred to as a very important second best allocation. We know that the first best is always to try to introduce error-diverse security to make the market complete, which is not always possible. So instead, the policymakers, they usually want to try to use some policy instrument to implement the second best allocation. This is very important, but very hard to solve in lots of heterogeneous agent models. So in the previous literature, people can only solve this constraint efficiency problem in heterogeneous agent model with no aggregate shock. So this was done by Davila, Hong, Crusoe, Rossrow in their 2012 Econometric paper, and also by Kendall and Bembo in their recent RED paper. So as I just say, so for our DPAM method, it's solving constraint efficiency problem is as easy as solving competitive equilibrium problem. We just need to remove this fictitious play procedure, in our algorithm. Essentially, we want to maximize, we want to optimize over everybody's policy function altogether, try to maximize the social welfare objective that the planner specified. So in the paper, we solved the constraint efficiency problem. So first with no aggregate shock, as people do in Davila et al. Econometric paper. But then we also solved this new problem with in constraint efficiency problem in models with aggregate shock and also countercyclical unemployment risk. So just to give you a sense about this power of deep learning method to solve this kind of problem. So previously, it takes the Davila et al. Method about more than 10 hours to run their Fortran code on my laptop, but now it only takes DPAM like 20 minutes to solve the same problem also on my laptop. So it's I guess we do see some efficiency gain here. Okay, so then let's talk about some economics when we look into those solutions. So this table presents some economy aggregate statistics to the solution of constraint efficiency problem in a model with no aggregate shock and with aggregate shock. So as a benchmark, so here we also present this market this economy moments when we solve these models in a competitive equilibrium. We call this as market economy. There is market economy versus planner's economy. So my favorite topic in high school. Okay, so first let's look at the first two columns. So when there was no aggregate shock in the economy, it's a well-known result from the Davila et al. Paper that when the economy is sort of properly calibrated to the U.S. economy, with a U.S. level of inequality in the economy, so the social planner always want to raise the average asset level by a lot. So why? So this is because in the competitive equilibrium, in the market economy of this kind of problem, so there is this so-called pecuniary externality when households make their own saving decision. Essentially, it is even after all the households have the same saving policy function, but when households make their individual saving decision, they would not consider sort of the marginal effect of their saving decision on the aggregate, factor prices, right? Even they do have impact on the aggregate factor prices. If you think about, we change everybody's saving policy function. If everybody saves more, then the aggregate, capital return is going to be lower, right? But when individuals make their individual saving decision, they will not consider this kind of marginal effect. So this leads to the so-called pecuniary externality. But when the social planner choose the saving decision for everyone, so if the social planner is a sort of a utilitarian social planner, they will consider this additional marginal effect, so that they want to ask people to sort of save more, so that the average wage return is going to be higher in this economy, but the average capital return is going to be lower. So this comes from the first order condition of the representative deferred problem. So which means that when we have higher wage but the lower capital return, so this is going to redistribute from the capital income earner to the labor income earner. As we know that usually in an economy, the capital income earner are usually the richer people. So essentially, this is try to redistribute from the rich guys to the poor guys in this economy. Okay, so that is why when we solve for a constraint efficiency problem in the model with no aggregate shock, we will see a huge increase in the average capital compared to the economy with competitive equilibrium. Yes.
I'm reading you a question here from How It's online. He said one of the previous slides, what exactly is the QA? So the Q of A function again. So if you use one generalized moment means like Russell-Smith, then it should be a straight 45-degree line. That's the question.
Straight for what?
So if you use one generalized moment mean like Russell-Smith, then it should be a straight 45-degree line. That's his question. So he asked what
no, it should not be the so first it's not the straight 45-degree line, right? So it's what we solved here. So so of course in Crusoe-Smith, because the household they are heterogeneous in asset, they are heterogeneous so in their distance to the boring constraint. So their marginal saving rate are different. So which makes them sort of it's not the best to have the first moment at the representation. Or he is saying that Crusoe-Smith method is 45-degree line or something. Or in the moment.
Yeah, so I read his question so he's just updating the question. So I think take it offline after
sure, yeah. Sure. I appreciate that he wake up so early. Yeah. So he's at Washington, I think. Okay, so now let me continue on this solution to constraint efficiency problem. So we have just talked about this constraint efficiency versus competitive equilibrium in the economy with no aggregate shock. Yes.
I was wondering where the word constraint optimum comes from, and would it be that it's constrained in the sense that the policymaker cannot tax to redistribute well? It feels like he is pushing overinvestment because it's his only way to make the poor less poor. Am I right?
So,
would in a model where you can also do other things to reduce inequality, would you get again these high assets?
Yeah, I realize that this constraint optimum is really a bad terminology in front of this audience, this very technical audience, because you immediately think about we are doing some constraint optimization problem. Actually, so I should be clear that this constraint means that in the economy, there is idiosyncratic shock, which is, there is boring constraint, which makes, the economy an incomplete market economy. So, and the social planner need to respect that part of market incompleteness. They cannot introduce sort of an insurance market, overcome that. That's what the constraint really means.
The boring constraint.
Yeah, it's a market incompleteness constraint. The boring constraint and also this idiosyncratic shocks and hits individual households. Yeah, so but thanks for clarifying on that. That's a great point. Yes.
For the constraint optimum, going from no aggregate shocks to aggregate shocks, the average assets decreases. Do you have intuition for that?
Yeah, so this is exactly I'm going to talk now. So now I think we are clear that in a model with no aggregate shock, the social planner want to raise the aggregate capital level to raise the average wage rate, dampen the average capital return so that they can redistribute from the capital income earner to the labor income earner. So this is what the social plan wants to do in the economy with no aggregate shock. Then let's look at the economy with aggregate shock. Again, if we compare these two columns for competitive equilibrium and constraint efficiency problem, we still see that it also increases sort of by some amount, but obviously it's not as much aggressive as in the economy with no aggregate shock. So why? So actually, so we think about this issue by looking at the sort of the saving decision in the economy with no aggregate shock versus in the economy with aggregate shock. We find that when the economy has aggregate shock and also counter-cyclical income risk, so everybody is actually going to save more against this additional aggregate shock, and also, of course, unemployment risk. So this kind of precautionary saving against aggregate shock makes people, especially low-income people, make everybody has a lower level of labor income share. I cannot remove it. Okay, so this is the blue line is the labor income share for the economy with no aggregate shock. So this orange line is the labor income share with aggregate shock. You can see that because of this additional precautionary saving motive, so everybody is actually going to have a lower level of labor income share. So especially you can see that like for people who are here, like below 10, so they are low and middle income people here. So this makes sort of makes it makes the social planner think that it's no longer we don't need to do that much of redistribution because now people have less labor income share, that even for low income people they have more asset, so that the social planner only need to they still need to raise the aggregate capital, but not as much as they need to do in the economy with no aggregate shock. Right. So it's like, yeah, it's because it's no longer that necessary. Okay, now I guess I will just quickly conclude, then taking more questions. So in this project, we developed this deep hand methods. One of the many methods that people are actually working in this field. I think that a couple of nice features that is, first we have some sort of interpretable generalized moments that tells us how distribution matter in heterogeneous agent economy. And also, I think importantly, for the first time, we are able to solve the constraint efficiency problem in heterogeneous agent model with aggregate shocks. So let's say, so usually this is an important benchmark for people to study when they want to design some optimal tax instrument, because essentially we want to design a tax instrument to achieve this kind of second best constraint efficiency allocation. Then I guess here I'm putting another quote. So I started with a quote from Richard as a heterogeneous agent models. It's one of the most important developments. So if you are interested in macro, you should work on it. So, then there's another quote from the finance people. So last year, the Review of Financial Study, they published a paper called Perspectives on the Future of Asset Pricing. In which they write that the neural network techniques will open up a new research avenue in macrofinance. So I guess a few possible directions that I'm working on, and I think people in this summer school are looking for topics to work on. I guess also valuable to explore. The first one is to think about asset pricing issues with rich heterogeneity. So obviously here we are all talking a lot about global solution methods, but obviously in the current heterogeneous agent model literature, sort of the dominant solution, I would say that many papers are local solution methods. So one place that I think the local solution methods cannot capture is about those rich nonlinearities and especially to think about like asset pricing issues in these kind of models, so which I think is, like opens up. So with these deep learning methods, it opens up a new research avenue. And also, so I was talking about this constraint efficiency problem. This is very related to what people are currently working with, the so-called heterogeneous agent Yucheng model, HANK model. So here NK doesn't mean a Newton counterage. I didn't know that the NK has another meaning. So HANK models, so many people are working. So I think there's lots of interest when we think about optimal monetary fiscal policy design, but also at the same time thinking about the redistribution issue. Then this is very important to have some deep learning methods to study the welfare issue in this kind of models. And also, this kind of Crusoe-Smith model, incomplete market heterogeneous agent model, it has some particular feature that heterogeneity actually affect the individual decisions through some aggregate price path. So which means fundamentally there are some like low dimensional representation in the nature of this model. So there are another very important kind of heterogeneous agent model, which is the so-called search and matching model. Where many people work on that. So these models, they actually also have lots of heterogeneity, but the heterogeneity matters in a very different way. So it's not through price, but sort of through the matching probability for the whole bunch of people with me. So it's like it's harder for this kind of problem for us to find some low dimensional representation, which makes if we can use deep learning, it's going to could be very powerful in terms of solving this class of model. This model is also very related to the recent literature on models with rich spatial structure. So I think on Friday I'm going to present some of our attempt to use deep learning to study this model, which we call as DeepSet. So it's a brother or sister of the DeepSet methods. So we are doing. So I just find it's very fun to work on this kind of issues. I hope you also find it's fun to try some of it. Yes.
Like two kind of questions. So first, do you have like a hunch on whether your method, like you use these finite agent assumption, could there also be like a version where you do it with this kind of discretized distribution and like an infinite amount of agents? I would think that, for example, this picture display step could be like adjusted, for example, for such a case.
So my understanding is, I think Simon is working. Deep equilibrium net is based on discretization over the state vector. So I think it's also another way to do that. But you already see that actually with finite agent we can do this fictitious play versus non-fictitious play. I think this.
We have that in the paper. Also version for that.
Okay. Is there going to be some metrical code?
Oh yeah, but so we didn't prepare notebooks, but we have code. So let me know if any of you need our code. We are happy to share the code with you.